Hi, everyone. Thanks for your interest in our paper on improving 2D to 3D object pose estimation accuracy via crowdsourced joint object estimation. I'm Jean, your presenter today. Extracting precise 3D information from 2D images to create high-quality 3D dataset is a grand challenge for computer vision researchers. Oftentimes, this conversion of 2D to 3D involves manual annotations to help the computation. For example, annotations on where the object's bounds are or how tall the object is in real world. However, even with these help, finding the true 3D location of an object is a challenging optimization problem because the unknown parameters makes it an underdetermined system and the annotation noise is unavoidable due to various factors. This makes the optimizer to have to search for a solution in a large space, making it hard to approximate the ground truth. And the problem gets even more challenging if it's difficult to annotate on the target object due to the object being too small or being occluded. Therefore, we propose an idea on referring to neighboring objects that appear in the scene with the target object. Our idea is that based on the information from these diverse different in-scene objects, we will be able to narrow down the search space for the solution, making it easier to approximate the ground truth. Because people will have different perspective and knowledge on the objects, we are leveraging the diversity of crowd's answers so that we can achieve more accurate collective performance. Then our question is, how can we project the information from other objects to the target object? Our answer is to use the shared spatial relationship between the objects to project the information in the form of annotations to the target object. Next, we had a question on what form of knowledge to elicit from the annotators, and we choose to use the approximate measurements of objects such as the height, width, and length, because then people can refer to their own knowledge or search for the measurement if they can identify the object. We also used manually drawn dimensions lines to tie the measurement annotations to the pixels, as you see in this figure. Here is our system pipeline, and the purple box is where the additional knowledge from the in-scene objects are aggregated into the baseline system. We call these objects as reference objects since we refer to their information when estimating the location of a target object. To elicit diverse measurement estimations from the annotators, we came up with different answer types based on 3 categories. For example, a worker can give the information like the object is about 10% longer than the target object, which is the relative length given in a single value answer. Here is the worker interface that consists of 3 steps. Using the CrowdWorkers annotation, our goal is to find the location of a 3D bounding box whose projection onto the 3D image has minimum distance with the annotated dimension lines. To minimize the distance between these two, we used an optimizer with the above cost function. And now what we propose is to add a penalty function to the cost function so that the added penalty function creates a soft constraint for the optimizer to guide finding a better solution. And this penalty function is created using the approximate measurements from the reference object in the scene, colored in green. To understand the effectiveness of our proposed approach, we ran a control study. We first ran it for the baseline method, which doesn't have the penalty function. And the result shows that there is a 65% of average noise floor, even with 0 annotation noise in the target object. But if we ran the same study with the proposed method, which uses the penalty function, the noise floor can be reduced to 0 theoretically. Next, we ran an actual study with the full end-to-end pipeline and recruiting MTurk crowd workers. We prepared 15 synthesized test images, like the one in the slide, and asked the workers to annotate the target object and the reference object. We compared the result of collecting 10 total annotations, where the baseline had annotations from only the target object, and the proposed method had it from both the target object and the reference object. As a result, we got 40% error reduction. And because the task time for reference object annotation was only 35% of that of the target object annotation, we can say that our proposed method was not only more accurate, but was also more efficient. Thank you.